Classic astronomy is visual astronomy, optical astronomy. That's what we do with our eyes, and that's what Galileo did with the first telescope. And for the first couple of 100 years, visual astronomy was all that there was. Astronomy at other wavelengths was invented in the first part of the 20th century when the technologies to detect radio waves and then X-rays and gamma rays and ultraviolet and infrared waves were all developed over a period of a few decades. The invisible parts of the electromagnetic spectrum tell us a lot about how the universe works. Imagine you had a piano and all you could make was the music with two adjacent white keys. A factor of 2 in optical wavelength from the bluest blue to the reddest red is all we can see with our eyes. The electromagnetic spectrum, all of it, would be like playing the full piano keyboard. Imagine the richness of the music compared to just 2 adjacent notes. We want to gather all that information, which requires different facilities and different techniques in the different wavelength regimes. Over a period of time, astronomers have pried open the entire electromagnetic spectrum, a factor of 1 trillion in wavelength, from tiny gamma rays, smaller than the size of an atomic nucleus, to meter-length radio waves. Some classes or types of astronomical object have been observed at all wavelengths between gamma rays and radio waves. It's an extraordinary wealth of information, and the invisible universe is responsible for informing us a lot about how the universe works. Optical astronomers do like to boast about their large telescopes. I've already done a little bit of that. But radio astronomers are happy to remind us that they indeed have the world's largest telescope, and have had for 50 years or more. Down in Puerto Rico, there's a dish called the Arecibo dish, which is 300 meters in diameter, just over 1,000 feet, an extraordinary size for any telescope. This dish is familiar because it's featured in several movies, including the movie Contact. Arecibo was built in the early 1950s, a fantastic engineering undertaking, and it was operated by Cornell University for most of the past half-century. It's not steerable at all because it sits in a natural depression in limestone country in the central part of the Puerto Rican island, karst country. Using aerial images, cartographers figured out where the place that most naturally fit the shape of a telescope was, and by moving relatively small amounts of dirt and rock, they were able to put a metal mesh dish in place. Since it's too heavy and massive and large to steer, this dish points at one spot over the sky, and as the Earth rotates and then moves around the Sun, it tracks out a swath of sky that it can study. But it can't look at far northern or far southern declinations or latitudes. An aerial image of the Arecibo dish indicates the scale of the operation. The 3 towers at the corners are each the size of the Washington Monument. The radiation is collected after bouncing off the mesh at a feed, called the Gregorian feed, that is suspended by cables above the dish. I visited the facility, and it's a vertigo-inducing experience to walk out on a narrow catwalk to the dish suspended a football field's length above the dish itself. People who've worked at the Arecibo radio telescope like to point out its immensity. 2 examples I've heard are that if you filled it with 300 million boxes of cornflakes, you'd fill it up to the top. Another is that the dish could contain all the beer drunk on Earth in one day. But radio astronomers have dreams of bigger telescopes too. And for the next decade, they're planning something called the Square Kilometer Array. The Square Kilometer Array, or SKA, will improve on the best sensitivity of current radio telescopes, like the Very Large Array in New Mexico, by 2 orders of magnitude, a factor of 100. 18 countries are involved in this consortium. It's a multi-billion-dollar project involving 8,000 separate radio antennae. There was a contentious and occasionally bitter debate over where the telescope should be situated. In the end, it was declared a tie, and the facility will be distributed between Australia and South Africa. This is by far the largest ever scientific project awarded to an African country, and so is a landmark in those terms. Somewhat longer than the wavelengths that the eye can see, but shorter than radio wavelengths, are infrared waves. Short infrared waves do penetrate to the Earth's surface, and high-altitude observatories like Mauna Kea and the Chilean sites are able to do near-infrared astronomy. But for mid- and far-infrared astronomy, wavelengths like 10 microns and longer, you need either to go into space or to very high altitudes. These altitudes can be reached by aircraft and by balloons. The Spitzer Space Telescope is NASA's contribution to infrared astronomy, nearing the end of its mission because its cryogenic coolant is exhausted and it's now in a warm mode. Meanwhile, NASA has A space observatory using an airplane, a Jumbo SP, where the back part of the Jumbo is carved out and a 3-meter telescope is inserted near the tail of the aircraft. This seems implausible. The last thing you imagine flying a Jumbo is with a great gaping hole in its tail and a telescope pointing out. But the aerodynamics have been worked out carefully, and this telescope has now been commissioned and tested, and it can indeed point stably at the sky while the aircraft is flying at hundreds of miles an hour. The altitude of these flights are quite high, 45 to 48,000 feet, above most of the atmosphere that can absorb infrared radiation. Typically, this kind of a plane will do flights of 3 to 5 hours on preordained paths that let it look at particular astronomical targets at night, and it will do perhaps 24 flights a year. Teachers are involved in many of the scientific programs, and sometimes they're students too, so more than just professional astronomers are getting the extraordinary experience of doing astronomy at night at 48,000 feet from a jumbo jet. At the shortest invisible wavelengths we have X-rays. The Chandra X-ray Observatory is still doing wonderful work into its second decade, but astronomers have dreams of other large X-ray telescopes too. X-rays mirrors work in a different way from optical and infrared mirrors. X-rays would be absorbed by a glass surface if they fell directly on it. So an X-ray telescope works by what's called grazing incidence. The X-rays arrive at a very shallow angle and are reflected at an equal shallow angle. So multiple reflections are required, and nested arrays of mirrors are required to steadily gather the X-rays to a focal point. This requires a lot of concentric reflecting surfaces, so the hardware involved in an X-ray telescope is large, complex, and expensive, and it's hard to use this method to simulate a very large collecting area. Therefore, X-ray telescopes never rival optical or infrared telescopes in their collecting area. But the information is extremely valuable because X-rays, of course, do not penetrate to the ground. This work can only be done in space. We can get a sense of the diversity of scientific topics addressed by the Chandra X-ray Observatory, one of NASA's great observatories. Think of it as the high-frequency, high-energy counterpart to the Hubble Space Telescope. Modern astronomy depends on detecting invisible waves. The visible spectrum from the bluest blue to the reddest red that you can see is barely a factor of 2 in wavelength. Yet there's a factor of 1 trillion in wavelength from gamma rays to radio waves which emerge from the universe and from which we can learn. Telescopes have been constructed in space to detect those high-frequency forms of radiation that do not reach the Earth's surface. The long-wavelength forms of radiation, radio waves, do reach the Earth's surface, and radio astronomers have their eyes set on huge arrays of telescopes involving thousands of dishes working in concert to observe the deep universe. Infrared astronomy is done from high mountaintops, or using balloons, or high-flying aircraft, or also from space. All of these invisible forms of radiation are used in concert to learn about astronomical objects.